Good afternoon. Welcome back to Codex. Many, but not all, of our talks this summer feature graduate students and postdocs who were nominated to speak by their senior colleagues. Today, we're very happy to have Victor Bailey be the next in this series. Victor is currently a graduate student at Georgia Tech, working with Chris Heil, and planning on graduating this year. So I assume he'll be on the job market very soon. His research focuses on problems in dynamical sampling. We're excited to have him here to tell us about frames via unilateral iterations of bounded operators. Take it away, Victor.
All right. Yes, thank you, John. I'll be talking about frames obtained by one-sided iterations of bounded operators. I want to thank the organizers of Codex for the opportunity to give this talk. And I want to mention this is joint work with Carlos Cabrelli from the University of Buenos Aires. Also want to mention some of the main contributors to the area of dynamical sampling, these names that you see here: Asekal, Druby, Cabrelli, Christensen, Cornelson, and so on. So just a bit of background for this talk. We define the Hardy-Hilbert space on the torus as this particular set that you see here. It's a collection of functions in L2 of the torus such that these integrals here are negative or zero whenever this power here is negative. So these are precisely functions in L2 of the torus such that their negative Fourier coefficients are zero. Given you have some function in the Hardy-Hilbert space on the torus, that function can be written as a power series in the way we see there, where these scalars Cn form an L2 sequence. An inner function is just some function in the Hardy-Hilbert space such that its absolute value is 1 almost everywhere on the torus. Given a separable Hilbert space and some bounded operator taking it from itself to itself, we say we have an invariant subspace of that operator if it's a closed subspace that gets mapped back into itself by that operator. So here's a groundbreaking theorem by Berling. It says that every invariant subspace of the shift operator on the Hardy-Hilbert space, where this is exactly what the shift operator does, it's of the form some inner function times the Hardy-Hilbert space, the entire space there. Conversely, if you have some inner function, you define a subspace this way, necessarily that subspace is going to be invariant under that shift operator. So what is this theorem saying? Why is it so deep? Well, this theorem is saying that whenever you have some closed subspace of the Hardy-Hilbert space that happens to get mapped back into itself by that shift operator, then necessarily every element of that space can be represented as some fixed inner function times some element of the Hardy-Hilbert space. All right, this is a deep result and it'll be used heavily in this talk. So just some background about frames. Frame is just a countable collection of vectors in some separable Hilbert space such that this inequality is satisfied for every f and h, every element of the Hilbert space. What's it saying here? The L2 norm squared of the sequence of inner products of the frame vectors with every f and h must be bounded above and below in the way that we see there for some fixed positive constants. This upper bound tells us immediately that this frame must be a Bessel sequence. The lower bound, we can glean from that a frame must be a complete set in your Hilbert space. But something that's not immediately apparent, but that all frames do, is that they admit these basis-like expansions of our elements within the Hilbert space. Okay, and so that's what's really nice about frames is that they do this, but like I said just a second ago, they're basis-like expansions. So we know that bases also admit this sort of expansion for your elements inside your Hilbert space. But what's nice about frames is that they're not necessarily, they don't have to be minimal, so that these expansions, these reconstructions of our of our vectors in the Hilbert space are not necessarily unique. So these scalars CK, they can vary. And that's something that, allowing these multiple ways to reconstruct vectors inside your Hilbert space using the frame vectors, that's something that makes frames very useful in practice and interesting objects in their own right. Here are some operators that are going to be used in this talk. We have the synthesis operator. It takes us from L2 into H. This way, it forms a series using the scalars from the L2 sequence. Here's its adjoint, the analysis operator. It takes us from H into L2 by mapping our vector into the sequence of inner products with the frame vectors. The frame operator is just the product of the synthesis and analysis operators in the order that we see here. It's a bounded operator. It's invertible, self-adjoint and positive, and this is exactly what it does. In the series, it converges for every frame, if you're given a frame defining that frame operator. The canonical dual frame of a frame is also a frame given these FK form a frame themselves. It's just defined by taking the inverse of the frame operator, applying it to the frame vectors. What's nice about the canonical dual is that it allows us to form these explicit reconstructions of our vectors inside the Hilbert space using the canonical dual in the frame, in the original frame itself. Of course, you can obtain the same reconstruction by interchanging the roles of those two. A read sequence is just a collection of vectors inside your Hilbert space that happens to form a bounded unconditional basis for its own span closure. If that sequence is complete, we call it a read. Okay, so just some more background for this talk, the sampling theory in general. Typically, in sampling theory, what one looks to do is recover functions or reconstruct functions using samples or values of that function at certain points within its domain, and taking that information, you look for a way to recover the function altogether across its entire domain. So this particular theorem, it's a classical sampling theorem. We see this kind of idea being applied. If you have some values, m and omega satisfy some inequality, you have some function inside some Paley-Wiener space satisfying these particular properties here, these conditions, then we have that there's a way to recover any f inside of this Paley-Wiener space, given we sample that function at these points in M, as n ranges over all the integers, and by taking into account this function, this term, and that other value there. So what we're seeing here is that by sampling the function at these points in M, these infinitely many points, there is some kind of way to recover the function altogether that we're interested in. And that's great. It's great that we can take some countable set, in this case, a countably infinite set of points, and evaluate the function at those points and find a way to recover the function across its domain. However, this sort of idea leaves a bit to be desired in that sometimes in practice, we may not be afforded so many samples. We saw in M is n ranged over the integers there. So for that reason, in a paper by authors Vetterli and Liu, they actually came up with a way to reconstruct functions using an insufficient spatial sampling density. Insufficient in the sense that it's, you're afforded fewer values than perhaps in that theorem that we saw just a moment ago. And the way they did this was they took a function and they took the limited number of points that they had to sample the function at, and they took some operator, some bounded operator that gave the function's future state in time, and by sampling the original function at those points that they were afforded and its evolved versions of the function, by doing that, they found a way to take all together those time-space samples by iterating that operator and sampling at those same points. They took all together those time-space samples and found a way to recover the functions that they were interested in. So in dynamical sampling, a similar thing is done, only we now do away with any notion of domain, and we look to reconstruct vectors inside of abstract Hilbert spaces. And what we do then is we still take the function and its evolved versions under some bounded operator, but instead of sampling the function at points within its domain, we take inner products of those functions with some vectors coming from a countable subset of our Hilbert space. So we ask ourselves, when is this enough information for recovery of the functions that we're interested in, or when is that enough information to get F? Well, the nice thing you can note is that by the definition of the adjoint of an operator, these values here are the exact same as these on the right-hand side of the equality. Just by applying the adjoint operator to G, we can move this guy over and obtain that. So that if you think back to your frame inequality, you'll realize that this is enough information for stable reconstruction or stable recovery of our function, if and only if this collection of vectors happens to form a frame for our Hilbert space. So we can find any F and H using this sort of information, if and only if these guys form a frame for our Hilbert space. And that's really the heart of dynamical sampling. The question really is, when does a system like this, iterations of some bounded operator on some set of vectors, when does that system form a frame or a basis or a particular set that is helpful for us in reconstructing our Hilbert space? So the dynamical sampling problem itself was that's that same problem, finding conditions for systems like that to form a frame or a basis or so on. That the problem itself was completely solved for the finite dimensional setting in this particular paper by these authors. And so we turn our attention to the infinite dimensional Hilbert space setting. In particular, separable infinite dimensional Hilbert spaces we'll be dealing with. And the question here, and what we have a lot of work and results on is the problem phrased in this way or given in this way. If we have some bounded operator and just some vector inside of our Hilbert space, what are conditions necessary and sufficient perhaps, such that a system like this can be a frame or a basis? What are conditions for it to be Bessel, complete, minimal, etc.? Really, like I said, what are conditions for a system like this to be useful somehow in us recovering our Hilbert space? So, of course, there's a large body of work in this area, and in the literature there are many results, and it's sad to say, though, a lot of these results are actually negative results, and so we can look at this sort of lengthy list of negative results and kind of see that being displayed. So, in particular, when the operator happens to be normal, that sort of iterated system that we've been talking about, it's been shown by these authors that a system like that can never be a basis. Now, what was shown was a system like this can never be both complete and minimal at the same time when the operator is normal. And since all bases are exact sequences, they're both complete and minimal. A guy like this for T normal can't be a basis. If your operator is unitary, it's been shown that a system like this can never be a frame. If your operator is compact, and remember we're talking about here infinite dimensional Hilbert spaces. So if your operator is compact, then this sort of system can never be a frame. If the operator is hypercyclic, that is to say if iterations of the operator on any vector happens to form a dense subset of your Hilbert space, then a system like this for any phi can never be a frame. Also, it's been shown that if T is self-adjoint, then this system, it's just a normalized version of the system we've been considering, can never be a frame. And it's actually conjectured, it's an open problem, that this is the case when T is normal as well, that a system like that, the normalized system, can't be a frame given T is normal. So, in light of all those negative results, it kind of begs the question as to, how likely is it that we can find frames that look like this, that have this sort of iterated system kind of form? Or, even, given a frame, is there some kind of way, is it likely for there to be some kind of way for that frame to exhibit this sort of iterated system form? It really begs the question of how likely it is that we can even find frames that look like this. And so a great step in the direction to kind of answering that question was by these authors here, Christensen and Asanasab. And in the particular paper, what they showed is the following. A frame, just a given frame, can be written in this particular form, this iterated system form, if and only if that frame is finitely linearly independent. Okay, so what they showed then is whenever you have a system like this that is forming a frame necessarily, that frame is a linearly independent frame, but then also if you're given a frame, it happens to be finitely linearly independent, there is some sort of way that you can construct this iterated system form for that particular frame. You can rewrite it in this way. However, what these authors showed was that this can be done using just some linear operator, not necessarily a bounded operator. So what they've shown is that, yes, whenever you have a system like this, when the operator is bounded to, well, then necessarily that system has to be linearly independent. But all this theorem is showing in the other direction is that if the system's linearly independent, then it can be given in this form, just with a linear operator, not necessarily bounded. And I mentioned that because the dynamical sampling problem really is focused on whether or not you can find frames of this form using a bounded operator. And for that reason, authors Christensen and Asanasab took it a step further, and they showed that a frame can look like this, can admit this form, if with the operator being bounded, if and only if the kernel of the synthesis operator of that frame is an invariant subspace of this particular right shift operator, of the right shift operator on L2, which is this operator right here. Okay, so this result, I mean, it's a very nice result because it tells us exactly when a frame can exhibit this particular form, the form that's what we're using or looking at in dynamical sampling. But the result is somewhat a striking result in the sense that it's kind of unclear where this sort of comes from. I mean, what's it saying? It's saying that a frame can look like this with a bounded operator if and only if some particular subspace of L2 happens to get mapped back into itself by some particular operator. It's kind of unclear where that comes from. And it's a striking result for that reason. However, the seemingly obscure result is one that connects dynamical sampling to the theory of Hardy-Hilbert spaces. And it really allows us to find necessary and sufficient conditions for a system like this to be a frame with T-bounded.
I'm sorry, Victor, can you go back?
Yes.
I may have missed something. What is U here?
U is the synthesis operator.
Oh, okay, all right, thanks.
Of course. All right, so a theorem from my paper that's kind of in the same vein as those theorems that we just saw is the following. A frame admits this particular form with T-bounded if and only if that frame is a Rees basis or it's a linearly independent frame and the kernel of the synthesis operator for that frame is generated by vectors like this, right? Iterations of the right shift operator on some particular scalar sequence, such that L2 sequence, such that the image of that sequence is some inner function within the Hardy-Hilbert space. So that was a bit of a mouthful. So what's this theorem really saying? Let's kind of think about this here and talk about it. It's saying that given the frame admits this form, okay, then these things must hold. And let's just take a second to analyze these two separate cases. It's actually the case that whenever your frame is a minimal frame, okay, that is to say the frame is a Rees basis, whenever it's a minimal frame can always admit this form. Why is that the case? That's the case because, first of all, minimal frame will be linearly independent, finitely linearly independent, and the kernel of the synthesis operator will just be 0 in that case. And of course, that set is going to be right shift invariant. So when we talk about these two different cases, really the interesting case is this one here, not so much the Rees basis case. So let's talk about then this theorem and just consider the case where we're talking about the frame being overcomplete. Okay, not minimal. So assume that the frame admits this form and the frame is overcomplete. Okay, well, then we're talking about this case here. And so what happens here? Well, if the frame is overcomplete, okay, then the kernel of the synthesis operator is going to be non-trivial. All right, so it's a non-trivial subspace, and since we're saying we're writing the frame in this form, then the kernel of the synthesis operator will then be invariant under the right shift operator on L2. Well, it's actually the case that invariant subspaces of that right shift operator on L2, they correspond to invariant subspaces of the shift operator on the Hardy-Hilbert space, that shift operator that we talked about at the beginning, by this particular unitary map A. So that given this guy here is non-trivial and right shift invariant, by Berling's theorem, the corresponding subspace via this map A, the corresponding subspace to this guy, the subspace that's invariant under the multiplication operator, the shift operator, MZ, we'll assume this form by Berling's theorem. Okay, so what am I saying? I'm saying that the image of this guy will look like this for some particular inner function. Okay, given we assume that the frame admits this form, it's an overcomplete frame. Okay, all right. Well, so how do we get the conclusion, the rest of the statement there in the theorem? Well, it's actually the case that subspaces of this form, they are actually they are cyclic subspaces of the multiplication operator, that shift operator MZ, so that this guy is actually just this. He's generated by, this subspace is generated by this particular set. It's by those vectors. So that then, as we can see here, so that then applying the inverse of that unitary map A, we obtain that this guy, the kernel of the synthesis operator, will be generated by those particular vectors. So given Berling's theorem and those things, it's kind of apparent that this would take place. But what's interesting to note is that what we've shown here is that whenever the frame is an overcomplete frame and it emits this form, then necessarily that subspace that determines whether or not the frame can admit this form with a bounded operator also is generated by vectors that assume that exact same form. So this theorem is, it is a necessary and sufficient condition that's being given here. More details for you to see in the paper. It's on archive, but I just want to continue on so we can talk about some more nice results. So from now on, let's just drop the distinction between that operator MZ and the operator S. So now when we talk about S, we're not talking about the right shift operator on L2, we're talking about the shift on the Hardy-Hilbert space on the torus. Okay, so just some definitions that we need. Model space, what is that? It's a particular subspace of the Hardy-Hilbert space on the torus, such that it's defined by taking the orthogonal complement of some shift invariant subspace. So it makes sense to denote a model space using the inner function because all shift invariant subspaces of the Hardy-Hilbert space assume this particular form. So that's what a model space is. It's just the orthogonal complement of some shift invariant subspace. Another definition here, this map S theta is known as the compression of the shift to K theta, where this guy PK theta is just the orthogonal projection onto the model space K theta. So what is this map doing? It's just you restrict the shift operator, the regular shift, to the model space. You apply the shift to that whatever vector you want, and then after you've done so, you project back into that model space. That's the compression of the shift. Definition here of finite Blaschke product is just some inner function that assumes this particular form, a finite product of terms like that here, where these lambda j, they come from the disk, and C is just some value in the torus. What's important to note is that the collection of finite Blaschke products forms a proper subset of the collection of all inner functions in the Hardy-Hilbert space. Okay. A few more things that we need in order to talk about this very nice result that's inspired Carlos and I's work. Here's another definition. Given you have two complex separable infinite dimensional Hilbert spaces, some bounded operator taking H from itself to itself, some bounded operator A taking the other space from itself to itself. All right, we say that pairs like this are similar, and we write this similarity relation here. Given there exists some bounded bijection, which is really going to be a topological isomorphism, taking us from H to K, such that conjugating the one operator by that map, you get the other one, A, and the image of the vector in the pair with the first operator is going to be the vector in the pair with the other operator. Okay, so just note that in order to use this definition, we need these Hilbert spaces to be infinite dimensional, complex separable, and so on. Okay, lemma for us. Okay, so if you have two pairs that are similar, then necessarily that iterated system that we've been considering this whole time forms a frame for the one space, if and only if the iterated system that we've been looking at forms a frame for the other space. Okay, we can actually take this lemma a step further and also note that a system like this, given this similarity holds, this system will be an overcomplete frame for its space, if and only if the other is an overcomplete frame for its space. Okay, now a lemma that's going to be useful to a model space, just the orthogonal complement of some shift invariant subspace. A model space is a finite dimension, if and only if the inner function defining that space is a finite Blaschke product. Okay. So if the inner function is not one of these finite Blaschke products, then necessarily the model space will have infinite dimension. And that is to say the invariant subspace will have infinite codimensions, same thing. Another lemma here, these guys are exactly the same here, and the system here forms a Parseval frame for our model space, given, you define some model space here. Okay, this is clear to see because these guys, z to the n, they form an orthonormal basis for the Hardy-Hilbert space on the torus. So that projecting each of those vectors into the model space, we end up with a Parseval frame. Okay, the thing to note is that iterations of the compression of the shift onto this particular vector is the same as these guys, and that system forms a Parseval frame for the model space. Okay, all that so that we can talk about this nice result by authors Christensen, Asanasov, and Philip. Okay, and this is really a result that characterizes when an overcomplete frame can, when a system like this will be an overcomplete frame. Necessary and sufficient conditions for that. Okay, what is the statement? It says that a system like this with T bounded, okay, which is what we've been interested in dynamical sampling, a system like this with T bounded will be an overcomplete frame if and only if we have the similarity relation being satisfied. So for some unique inner function, where unique just means it's unique up to a modulus 1 constant multiple, that is not a finite Blaschke product. Okay, so let's just talk about really quickly, when we say it's not a finite Blaschke product, that just tells us that the model space we'll be dealing with in the definition of the similarity will be infinite dimensional. Okay, so what do we have here? We have that, there are now, from this theorem, necessary and sufficient conditions for a system like this with T bounded to be an overcomplete frame for your Hilbert space. And what is this condition? It's that the operator that you iterate the vector inside your abstract Hilbert space on has to be similar to a compression of the shift operator in the Hardy-Hilbert space corresponding to some particular model space. So that's very deep results, very nice, that in your abstract Hilbert space, you can obtain an overcomplete frame this way, if and only if that operator is similar to a compression of the shift to some model space. Let's talk about the proof of this a little bit. All right, very quickly, this direction here, if you recall, just a moment ago, from the lemma that we saw that, you define some model space. If you take iterations of the compression of the shift applied to this particular vector, you end up with a Parseval frame for that model space. If you recall from that other lemma from before, that if this similarity relation is satisfied, then necessarily you get a frame of iterations using this operator and that vector for its space, if and only if iterations of this operator on this vector forms a frame for its space. And since this Parseval frame is going to be an overcomplete frame for that model space, this one here, this system is going to be an overcomplete frame as well. So that was assuming this relation held, and it implied this, okay? Now, let's talk about the other direction. Assume that this system forms an overcomplete frame, okay, where T is bounded. Okay, well, the things to note are that when this is an overcomplete frame, then of course, the kernel of the synthesis operator will be non-trivial, okay? And since the operator is bounded, we know it's going to be right shift invariant. And if you define this particular map, V as the Fourier transform first, and then the synthesis operator, we get a map that's taking us from the Hardy-Hilbert space into our abstract Hilbert space H. And this map will then be, its kernel will then be an invariant subspace of the shift operator defined on the Hardy-Hilbert space. So the kernel of this guy is going to be an invariant subspace of the shift on the Hardy-Hilbert space. And therefore, by Berling's theorem, that particular subspace will assume this form for some inner function. Okay. Now, the thing to note, though, too, is that this map V is going to be a surjective map. We're applying the Fourier transform to, just any vector inside the Hardy-Hilbert space. And then we take U and we, map into H. It's going to be a surjective map. And since that's the case, its kernel is going to have infinite codimension. Okay, so its orthogonal complement has to have infinite dimension. From that, if you set your model space as the orthogonal complement of that particular subspace, that kernel of V, and if you define this map W to be the restriction of V to the model space, then what do we obtain? We obtain everything in that definition of similarity. We've got a map taking a topological isomorphism taking us from K to H. The image of this particular vector will be this. And if we conjugate the compression of the shift this way, we'll end up with T. Okay, so this is a very nice result. And it gives us necessary and sufficient conditions for a system like that, for a bounded operator, an overcomplete frame, to form a frame. For a system like this, using a bounded operator to form an overcomplete frame. Okay. So, and that's very nice. I mean, that's what the whole question in dynamical sampling, kind of is. It's, what are conditions for iterations of some bounded operator on some vectors to form a frame? That particular theorem tackles the case where the frame would be overcomplete. And it also is restricted to the case where we're talking about iterations on one vector. But we do see here that, from that theorem, we obtain necessary and sufficient conditions so that the system that we've been interested in, it's not the only way that you can form this sort of system, but the type of system we've been interested in to form a frame. And so that's great. And it really is nice because it shows that, that the operators, they have to, satisfy a very specific condition. They have to be similar to a compression of the shift. And so, it's of interest, though, too, to ask ourselves, what perhaps are conditions where you use more than one operator to iterate on the vector and form a frame, for something like that, iterations like that on that vector to form a frame. In particular, you've got systems, that are generated by translations and modulations, and Gauber systems in particular. And we see those applied to some vector, and there's a lot of work that's been done to determine exactly when those guys are frames. And so it's of interest to ask ourselves, when do systems generated by more than one bounded operator applied to some vector, when do those form a frame? And so a nice first step in that particular direction to maybe classifying when two bounded operators iterated on some vector form a frame is to perhaps just consider the simpler case, the straightforward case, more straightforward, I guess, case of when these guys commute, those operators, T1 and T2 that we see here coming into play. And so just something that, is of interest is to find necessary and sufficient conditions for a system like this to be a frame. And from the work that we just saw a moment ago, that theorem we just saw, we now know that an iterated system using one operator applied to some vector, some bounded operator applied to some vector forming an overcomplete frame, you needed that operator to be similar to a compression of the shift on some model space. And so when we talk about two operators being applied to some vector, perhaps we need two shifts, for these guys to be similar to in order to obtain a sort of necessary and sufficient condition, sort of in the vein of the one that we just saw a moment ago. And so, unfortunately, on the Hardy-Hilbert space on the torus, there aren't two shifts available for us. But if we take a look at the Hardy-Hilbert space on the torus squared, there are actually two shifts, and perhaps there's some sort of way to find necessary and sufficient conditions so that systems like these could be a frame in a way similar to the theorem we just saw a moment ago. And so the Hardy-Hilbert space on the torus squared, what is that? It's a collection of vectors in L2 of the torus squared, such that these integrals are 0 whenever either of these powers are negative. Okay, so a similar definition as the Hardy-Hilbert space on the torus. Given a function in this space, okay, you can write that function as a power series in terms of the powers z and w, and these sequences here, these scalars, they form an L2 sequence as well in this setting. All right, a subspace of the Hardy-Hilbert space on the torus squared is said to be shift invariant in this particular setting if it's invariant under both shifts, the shift in the z direction and the shift in the w direction. Okay, so this is what we're seeing here. Okay. An inner function in this particular space is a function inside of the Hardy-Hilbert space on the torus squared, such that its absolute value is 1 almost everywhere on the torus squared, where this almost everywhere is the measure we're talking about is Lebesgue measure normalized. Okay. Now, since we've talked about, inner functions here, you may be thinking, okay, well, so just like in the theorem before, you're going to, have these Berling type invariant subspaces, and we're going to work with that, and it's going to be so clear what to do. However, it's unfortunate, though, Berling's characterization of invariant subspaces, they don't really translate fully to this particular setting, the Hardy-Hilbert space on the torus squared. And so due to that, we can't really say that all these shift invariant subspaces have this nice form that we've been talking about. However, it is worthwhile taking a look into the literature to determine exactly when invariant subspaces assume this form, because we saw the inner function coming into play in that theorem from before. And so perhaps it would be useful in some way to determine when invariant subspaces look like this, so that we can obtain something similar to the theorem we found before. So just here's the definition, and here's from the literature exactly when these invariant subspaces of the Hardy-Hilbert space on the torus squared look like this, that invariance, a Berling type form. So first, the definition. A pair of isometries, V1 and V2, are said to doubly commute on your Hilbert space if, on some Hilbert space, if V1 commutes with V2 and V1 commutes with V2 star, its adjoint on the Hilbert space. This theorem here by Mandrakar, which tells us precisely when an invariant subspace of this particular space here is of that particular form, the Berling type form. We see here that a shift invariant subspace of the Hardy-Hilbert space on the torus squared looks like this, has that Berling type form with that function being an inner function, if and only if both shifts, S1 and S2, doubly commute on that particular invariant subspace. Okay, so now here we have a lemma that is going to tell us exactly when the kernel of that operator that we saw before, that operator being the product of the synthesis operator and the Fourier transform, assumes this particular form, that Berling type form. So let's talk about that. And why do we want to achieve this? Well, because that's what was used in that theorem from before, and we're trying to see if there's a way to use that sort of work to tell us exactly when a system like this is a frame. Okay, so if we assume that these guys here happen to form an overcomplete frame, all right, where T1 and T2 are bounded and commute, we define U to be the synthesis operator for that frame. And if we say R1 and R2 are the right shift operators applied on coming from this L2 subspace, where R1 is the right shift in the first component, R2 is the right shift in the second component. And so assume these things, let those things hold. If R1 and R2 happen to doubly commute on the kernel of the synthesis operator, then the invariant subspace that we are interested in, the invariant subspace of the Hardy-Hilbert space on torus squared, will then assume this form, this Berling type form, where phi is some inner function. Okay, so you may be asking yourself, is that really worth doing? Taking all that time, assume this regarding the kernel of the synthesis operator. You have these two operators, they need to doubly commute. Is it really worthwhile to assume all these things so that we can just obtain that this particular subspace looks like this? Well, it is worthwhile, actually. And why? Well, it comes into play, and the reason why is going to be apparent here in this particular statement. So if you think back a moment ago, the theorem that by Christensen, Asanosov, and Philip, what was needed was, they obtained that you had this invariant subspace, it had that Berling type form, and they had to say something specific regarding the inner function so that they ensured that the model space that you deal with in that particular theorem is of infinite dimension. Well, what we're about to see is it's worthwhile to take the time to make those conditions so that your invariant subspace has this form, because all invariant subspaces of this particular form, where this phi is not a constant, they have the property that their orthogonal complement, that is to say the model space associated with that invariant subspace, will have infinite dimension. And so that's very nice, because we get automatically, so long as this particular inner function is not a constant, we get automatically that the model space that we'll be dealing with in the theorem that we're developing here, that model space will have infinite dimension, and that was something that was needed in the theorem from before. So let's talk about how this happens. Okay, by authors Argowal, Douglas, and Clark. some things were shown in their paper, invariant subspaces on the polydisk. It showed that when phi is an inner function, okay, and you have any invariant subspace of the Hardy-Hilbert space, and when I say invariant, I mean invariant under both shifts. Well, you have this taking place with equality if and only if that particular inner function is constant. Okay, so that's something that they showed, and so what am I saying? I'm saying that whenever phi is not a constant, we do get that this guy gets mapped into itself. You know, it'll be a proper subset of this. But if phi is a constant, then phi times m is just m. That is to say, if phi is constant, we would see also that phi times the Hardy-Hilbert space itself would just be the full space. Okay. Something else that they showed that's very helpful for us is this particular statement. They showed that every invariant subspace that has, of the Hardy-Hilbert space on the torus square, that has finite codimension, that is to say it's an orthogonal complement, has finite dimension. Necessarily, one of these guys with finite codimension has full range. Okay, so I'm not going to define what full range is here. It doesn't really add anything to our result here, but it does allow us to conclude what I'm going to state in just a second. So by Mandrikar, it was actually shown that invariant subspaces with this Berling type form never have that property of being full range unless that inner function is constant. Okay, so that a Berling type invariant subspace will never have finite codimension. That is to say, its orthogonal complement will never have finite dimension unless phi is constant. Okay, so all invariant subspaces of this particular form satisfy this unless those subspaces are not proper subspaces, unless it's the full Hardy-Hilbert space itself. Okay, so that shows us why it's worthwhile to do this work to obtain these Berling type subspaces, not just because it's interesting, but also because we automatically get that the model space will have infinite dimension so long as that inner function is non-constant. Okay, that's something that we didn't have in the theorem from before. In the theorem from before, we had to assume that that inner function could not be a particular type of inner function, a finite Blaschke product. But here, all we need to say is that so long as the invariant subspace is not a proper subspace, or is not proper, that is to say the invariant subspace is the whole Hardy-Hilbert space, then so long as that's not the case, then the model space that you can define using that invariant subspace will have infinite dimension. So that's very nice, and it's needed so that we can apply that similarity relation, that definition of this similarity that we're going to see come into play here now. Okay, so here's a theorem by Cabrelli and myself. And so what do we have? Given a system like this, all right, iterations of two bounded operators that commute on some vector there, given a system like this where T1, T2 commute, and given that they satisfy the property that the right shift operators, the R1 and R2, the one in the first component, the other in the second component, doubly commute on the kernel of the synthesis operator, where this is the synthesis operator corresponding to this particular sequence. Okay, if we assume that, then this system is an overcomplete frame for the Hilbert space, if and only if there exists some non-constant inner function such that you get the same sort of similarity that we saw before between the two bounded operators that are commuting and forming this system here, and the compressions of the shift in the z direction and in the w direction. So we see here this s theta 1 is just the compression of that first shift in the z direction, compression of that shift to the model space, and s theta 2 is the compression of the other shift to that model space. Okay, and we have that the vector that you're pairing those two guys with is the same sort of vector that we saw before. The orthogonal projection of the indicator function once again, but now indicator function on this the torus square. Okay, so that there's the result that we have here, and really this result, as you can see, it's somewhat like a seamless extension of the result from before regarding iterations of a single operator, bounded operator on vector. And so once again, if you assume that this sort of similarity holds, Well, what we can see is that iterations of these guys here on this particular vector, they do, once again, they form an overcomplete frame or a Parseval frame also for the model space. And we can conclude then that this system here that we've been talking about will then form an overcomplete frame for its space. And if we give ourselves an overcomplete frame using iterations of these operators on some vector, well, then this similarity will then be the case. Okay, so once again, we see we get the similarity between these compressions of the shift given a system like this forms a frame, overcomplete frame for our Hilbert space. Now, a more general version of this theorem does hold without assuming that double commuting property. Okay, really what we do is, just put assumptions that make it so that this particular model space that we'll use, just the orthogonal complement of the invariant subspace that we'll use, will have infinite dimension. But so that theorem that we have, it holds without assuming that double commuting property. And that particular theorem, does give a characterization then of frames given by these iterations of bounded commuting operators on some vector. Okay. So our current work and future work in this particular area, the things that we're doing and looking to do, we want to characterize the set of bounded commuting operators such that for some vector inside of our Hilbert space, we get that system that we've been talking about will admit the double commuting property on the kernel of the synthesis operator. Why do we want that? Well, we want that because we want to know which operators are the ones that allow us to use that particular theorem that we have. Okay. Next thing that we want to do is we want to apply the theory of model spaces to solve that open problem that I mentioned a while ago regarding iterations of a normal operator on some vector where those iterations on that vector are normalized so they all have norm 1. So what am I saying? I'm saying that we want to apply the theory of model spaces to answer that open question of when T is normal, can this guy be a frame? And so it's conjectured that that's not the case, that these guys can never be a frame, but perhaps there's a way using the same sort of theory of model space that we've been talking about in the Hardy-Hilbert space to solve this problem. And why? Why is this potentially applicable? Well, for every normal operator, we know by the spectral theorem that normal operator is unitarily equivalent to a direct sum of these same shift operators. The multiplication operator we saw before, these guys are similar. Every normal operator is similar to a direct sum of these shift operators, these multiplication operators on some L2 spaces, on direct sum of L2 spaces. So perhaps due to the fact that normal operators assume this or have this property, perhaps there's a way to use this theory of the shift operator that we've been talking about in the Hardy-Hilbert space to solve this open problem. Perhaps. Also, another thing that we're looking to do is to find necessary and sufficient conditions for systems given by iterations of bounded operators that nearly commute to be a frame. Okay. So just before I talked about the case where the operators commute, I mentioned Gauber systems. And in particular, Gauber systems, you have the modulation and translation. And although they don't commute, when you do interchange the order of those two operators, all you get is a modulus 1 term thrown in the mix. So perhaps, the theorem that we have, it doesn't apply to those sort of systems, but, maybe there's something that we can do to kind of get to determining necessary and sufficient conditions for systems like those, where the operators nearly commute to be a frame. All right, here's some references, and I'd like to thank you for your time and attention. Yeah. Thank you.
All right, let's smash that reaction button. Thanking Victor for his talk.